Flack math! Give me some math and I'll give you some flack. Flack math!
We're going to talk about the Pascal's triangle and use the binomial theorem. So, this is lesson 49. We're going to talk about the binomial theorem. Remember from geometry, a theorem is something that you can use in a proof, but this is something someone figured out and wrote it down, and we get to use it. Okay? So let's start with stuff that we already know. We actually did this in class. We taught this concept in Algebra 1 this morning. So what's a plus b squared? What are you doing?
What's the parenthesis like number over there again?
I don't know.
Okay.
So I think it's like 9 or something.
Hold on, I'll tell you.
It's on Schoology. I think it's 9 or
It's
something.
9, okay.
Because it's different. The numbers are different in each class, so I didn't put which one it is. I don't
Just
know.
pretend the P is a 9.
Okay, so do you guys remember doing this? Remember, this is not a squared plus b squared. You have to actually FOIL it out. Imagine they learned the acronym FOIL in Algebra 1. Remember those days? Good memories, good times. Okay, and then you FOIL it out, so you get a squared plus ab plus b squared. And you can always combine those middle terms. 2ab plus b squared. And remember, the shortcut was this squared, and then twice the product of these two terms. So 2ab. That's the shortcut to that. Well, what happens if you throw another exponent on it? So let's see what happens if I do this. So really, this is a squared plus 2ab plus b squared all times another a plus b. So then I get, let's see here, a cubed plus 2a squared b plus ab squared plus, all right, now multiply this. Oh, I was multiplying that by everything. Okay, so now b, so a squared b plus 2ab squared plus b cubed. Okay, so when you multiply all those out, this is what you get, and you can combine these together and these together, so you get a cubed plus 3a squared b plus 3ab squared plus b cubed. So it's a pain in the butt, right, doing that. So what we're going to talk about today is a shortcut to that. All right, so if I go backwards here, then I get a plus b to the 1. Well, that's just a plus b, right? Mm-hmm. Well, what's a plus b to the 0? Not nothing. 1. Anything to the 0 power is 1, right? Okay, so now if I just look at the coefficients of these things, a plus b to the 0, it's just 1. The coefficient of 1 is just 1. Remember, the coefficient is what the variable is being multiplied by. So this is technically, it could be 1 z to the 0 or whatever. So there is a variable there. It just is invisible because it has an exponent of 0. The coefficient of a constant is always itself. Okay? So 1. All right, look at the coefficient of these. What are the coefficients of A and B? Remember the coefficients? Do you know what I mean by coefficients?
Yeah, 1.
Yeah, these are both 1 and 1. So if I do this, I'm making a triangle. Okay, what about the 2 here? What are the coefficients of a squared, a plus b squared? Let's see, 1, 2, and 1. Okay, what about a plus b to the 3rd power? What are the coefficients here? 1, 3, 3, 1. Okay, and I'm going to write the next line without multiplying it out, and I want you to tell me how I got the next line. See how I'm getting that? Let me do the next one. Let me do the next one. I didn't have to memorize this. Who can tell me the next line?
177. How does six?
That's right. 1, 7, is right.
1720?
Yeah.
Is it 1720?
Not 20.
21.
21. How'd you get that?
I guess because I see a pattern.
What's the pattern?
Okay, so the first one is just 1, and the second one is just every other, whatever. And then the third one, it was adding 2, adding 3, adding 4, adding 5, and then adding 6.
Okay. Yeah, that works too.
Yeah.
There's an easier way, but good job.
I was guessing. So.
I know, you did great. You did great. That works, but there's an easier way. What's 1 plus 1?
2,
What's 1 plus 2?
3.
What's 1 plus 3? And what's 3 plus 3?
No,
Okay.
I was looking at this totally wrong.
So if I did this, a plus b, so remember this is exponent is 0. This is 1. This is 2, 3, 4, 5, 6. So now I can say a plus b to the 6th power is, now there's another aspect of this that you have to realize, that look at the degree, and this is written in standard form. Do you see what's happening? The degree of each of these terms is 2, but see how it's all in alphabetical order. These are all the combinations of an A and B. So AA, AB, BB. So see AA, AB, BB. Here's a AAA, AAB, ABB, and BBB. So see how these are all in alphabetical order? The A's go down and the B's go up. Okay? So let's do that. This is a to the 6. What's the first coefficient? 1. So I'm just going to leave it a to the 6. And then the next variable, what's the next variable term going to look like?
A to the 5th, B with the coefficient of 6.
Right. So then you'd use that coefficient. And then let's see, 15 is next. Then the A's go down, the B's go up.
Wait, are we doing to 6?
And then 20, let's see, the A's go down, the B's go up. 15, A's go down, B's go up. 6, A's go down, B's go up. And then one more, B to the 6. So there's 2 things you're doing. You have to figure out the coefficient by using the Pascal triangle. This is Pascal's triangle. He's the one who, hey, there's a pattern. When I build a triangle out of this, then every number below is the sum of the 2 numbers above it. This is Pascal's triangle. Okay? So you have to figure out the coefficients. And you just have to deal with the variables. Well, that's just writing everything in alphabetical order. Okay? But let's try this with something else. We're going to try this with an example that is using numbers instead of letters. When you're using letters, these numbers are nice. But when you're multiplying these things together and there's a number in there, these numbers aren't going to be those numbers. They're going to change because you're multiplying 20 times whatever this is. Well, if B was a number, then it'd be, that's what you're multiplying by, that number, and then this number squared, and then this number cubed. Okay, so I'll show you with an example. So here's the binomial theorem, and this is weird how it's written, but this is the binomial theorem. So a plus b to the n equals. So you have this constant. Oh, I can't read it all. So this is actually using the combination. maybe I won't write it that way. I can write it down, but we're not really going to use it this way. We're just going to figure it out. So you don't really have to use this theorem. I mean, you're going to use the theorem, but you're not going to use it like this. The first coefficient is a combination and then multiplied by a to the n and then b to the 0. So that combination is that number in the Pascal's triangle, okay? So don't worry about the combination part of it. Just the biggest thing, and I want you to pay attention to, is that the n's are going to go down and the b's are going to go up. So the next one is going to be still out of n possibilities, choosing 1, and then a to the n minus 1, b to the 1. Then it's going to go up all the way to the last term, which is picking n out of n objects, and then a to the 0, b to the n. Okay? And this is something that you'll see in calculus if you ever do calculus. This is basically a sum symbol. Again, don't stress about this. So this symbol just basically says follow this pattern. And it's the pattern that we've already talked about. So a to the n minus r, and then b to the r, where c, yeah, and then you already know c, how to do a combination, that formula. So confusing, right? But this isn't terrible. You just have to remember to start with 1, okay? And there's no numbers, so you're just 1. The hardest part about this triangle is these first 2 rows. Wait a minute, are those 1s or 0s? Well, if there were 0s, then you wouldn't get anywhere. Okay, so they're 1s, and then you start adding when you have numbers to add. Okay? All right, so let's do not a real life example, but an example where we can apply Pascal's triangle. So I'm going to leave Pascal's triangle up there. What do I not erase? That down there?
Just all of it. Let me take a picture.
Okay.
Like all of it.
And you can screenshot this when you watch my video.
Okay, thank you.
I'm gonna watch this a million times. Still
understanding
it. Camera's pointing over there.
No, the lens is in the front.
Oh.
It's kind of a weird deal.
Flashlight.
It's very small. It looks very nice, actually.
That works. You good? Everybody good?
No, but yeah.
Okay, so I'm going to leave.
I don't understand it.
Well, you'll understand once we do an example.
Okay.
That's usually the case.
That's true.
I'm a learn by example type of person too. I mean, I try to do both. I try to understand it and grasp it when someone tells me about it, but then I need to actually apply it to figure it out. So I love YouTube because they demonstrate. I mean, I love those guys. I used to think, like, dude, get a life. No. They're saving the world one YouTube video tutorial at a time. So, YouTube.
Just like everyone on
YouTube.
Yeah, I mean, obviously there's monetization that happens when you get views, but most of those guys are just doing it out of the goodness of their heart, not expecting anything. I'm like,
that's debatable.
God bless you. All right. So I'm going to skip. We already did example 2. So I'm going to skip to example 2b. Here's example 2b. This is 2r minus s cubed. Now we could just multiply this out. All right. But this binomial theorem is a shortcut. So if I go to the 3 here, here's what I'm going to write. I'm just going to write this line of coefficients. So it's going to be 1 times something plus 3 times something plus 3 times something plus 1 times something. Okay? Now here's the somethings. Is you're going to apply this exponent to this first term. So this is going to be 2r cubed. And then you're going to apply a 0 exponent to the s, okay? Or the negative s. Negative s to the 0. All right, so now the 2r's go down and the negative s's go up, the exponents, right? So what do I write next?
2r cubed, or sorry, squared.
2r squared.
Negative s to the 1.
Okay, awesome. All right, and then we're just adding everything. All right, what's next? 2r to the what? 1, and then negative s squared. So that's going to cancel that negative. That'll be nice. And then this one, the 2r's, you don't really have to write this because anything to the 0 is just 1. But it's just so you can see visually what's happening. Negative s to the 3rd. So see how the 2r's exponents went down and the negative s's went up. Okay? So this is the messy part. I would strongly recommend writing it out like this, even though it's a lot of work. And by this time, you probably would have been done by just multiplying binomial times binomial times binomial. But this is a good way to learn it with this small example. So let's do this math. This is 1. This is 1. So then we have 2r parenthesis cubed. What's 2r parenthesis cubed?
2r.
8r cubed. That's right. 2r times 2r times 2r is 8r cubed. And then 3 times, let's see, that's 4r squared times negative s. See what I did there? Okay, plus 3 times 2r times negative s, or negative s squared. What's negative s squared? Positive s squared, right? So negative times negative cancels. You're left with s squared plus just a negative s cubed, right? And technically a parenthesis there, but it's not going to affect anything. So let's see here. Let's simplify this. 8r cubed plus 12 plus negative 12r squared s. See where I got the negative? That negative.
That distributes to the whole thing.
Yep. Plus 6r s squared plus negative s cubed, or minus s cubed. So see how these numbers do not reflect these numbers, but they were multiplied because one of my terms had a coefficient in it. So if one or both have a coefficient in it, then these coefficients are going to be multiplied by those. So it's going to change the numbers. All right, so this is actually a way to find, like sometimes you'll be asked this. So we could have done this with any of these. We could have applied this to any of this. And by the time you get to 4 or 5, then this system becomes worth it. Over here, it might have been faster just to multiply the binomials, okay? But once you get down to 4 or 5 or 6, this definitely becomes worth it to use the Pascal's triangle. But what if I want to know a specific term? Okay, so what if I wanted to know, for example, p plus q to the 10th, and I wanted to know find the 5th term. So the 5th term, well, I can do that because none of these have coefficients. So I can just go down to the 10th here. Let's see here. I'm going to have to figure out that coefficient, or I could use the combination. So I could just keep writing the Pascal triangle, and if you Google this, you'll find one that goes down like 100 times, right? So you can find the 10th line. Actually, it's the 11th line if you want the 10th, because the first line is a 0 exponent. Okay, so you can find that 10th line and find that 5th term pretty easily, or you can use the combination. So this is going to be a combination of, let's see, out of 10 terms, I want a combination of this 10 exponent. Or no, I'm finding the 5th term. So I want to find that combination. Can't read. No, sorry, because the first term is a 0, so this is going to be the 4th one. I know that's confusing. So you can do it this way, or you could just look at the Pascal's triangle and then multiply it. But here's the deal. So we're going to do this combination times p to the basically 10 minus 4, and then q to the 4th. Okay, so let's do that. So the combination of 10 objects taken 4 at a time would be 10 factorial over 4 factorial times 10 minus 4 factorial, all times p to the 6th, q to the 4th. So this is the number that is represented in Pascal's triangle, if you were to look that up online. Okay, so if I do that, 10 factorial over 6 factorial times 4 factorial ends up being 210, p to the 6th, q to the 4th. Okay, you don't really have to do it that way. You don't have to use a combination. You could use Pascal's triangle. And if we were taking a test, then I will let you use that online, or if you want to print out Pascal's triangle, you can as well. But really on the test, you would have seen, okay, the 5th term over, that coefficient is 210. So we multiply 210 times this to the 4th, which is 1 less than, because you know the first one starts with 10 and it starts to go down. And then this to the 6th, or this to the 6th and this to the 4th. Okay, so you could do it either way you want, but this is, if you don't want to look it up, you can do it this way. All right. So there's another thing called binomial probability, which we could do if P is the probability of success of Q is of success, and Q is the probability of failure in one trial of a binomial experiment, then the binomial probability of exactly n successes in m trials is given combination of m objects taken n at a time, p to the n, q to the m minus n. So believe it or not, this is, people use this when they're trying to figure out probability of things happening in statistics, and they use the binomial theorem to do that. Okay, but we're not going to get that far. Let's move on to lesson 50. You guys good with all this?
No.
I mean, you need me to leave it up? Yeah, so remember, it really is just a shortcut, but the amount that it takes off when you're trying to find the 5th term in a binomial to the 10th power, it saves a lot of time. Because if you multiplied 10 binomials together and then located the 6th term or the 5th term, that would take you a while. But there's nothing wrong with that. Nothing at all. Okay. So this is lesson 50. So we're going to find inverses of relations and functions. Sounds confusing, but it's really rather simple. So take heart. Okay. Okay, so basically a relation is a set of ordered pairs. Okay, so a relation is a set of ordered pairs like x, y, or x and y can be whatever. Okay, so the inverse relation is just reversing. Inverse relation is just reversing that ordered pair. So the y goes in the x spot and the x goes in the y spot. Okay? Not too bad. All right. So remember, the multiplicative inverse is flipping something upside down. So the inverse of an ordered pair, you got to flip something. You can't flip upside down. That doesn't make sense. But they're written left and right, so just flip it. Left and right, it's flipped. Okay? So the inverse of a relationship may or may not be a function. Remember what determines a function? The vertical line test and things like that. So we call it an inverse relation if it's not a function. If a relation and its inverse are both functions, they are called inverse functions. Okay? So let's just try an example. So the first example says, describe this relation. Describe this relation. So basically, you're going to tell me if it's a function or not. Okay? So find the inverse. So here, let's see. The domain is x and y, right? And the range is y. So if I got 1, 1, 3, 2, 4, 5. Is this a function? No, because that 1 goes to both 2 and it goes to 4. Now, but if I did something like this, where if I had like a domain and range, if I had 1, 2, 3, all going to 4, 4, 4.
They're downstairs, though.
Is that a function? Okay, now tell me if the inverse is a function.
No.
No, because now 4 would go to 1, 4 would go to 2, and 4 would go to 3. But the normal function, it's a function, but when you invert it, it is no longer a function. So this is not an inverse function. Okay? But the inverse of this, would be a function. Okay? But this, yeah, so it has to both be a function to be able to be inverse functions. Okay. So what that looks like on a graph is the x and the y switch places. So for example, here is my, if I were to graph this, well, let's graph something else. Let's just put like, okay. So basically, if I reverse the x and y, if this was like 1, 2, then it'd be 2, 1. So it would look like this. If this is 1, 4, then it'd be 4, 1. Okay? So what do you think is going to happen? Well, It's going to look like this. So do you guys see the line of reflection? That line of reflection is this line. Do you know what this line is? What that is? This is y equals x. Slope-intercept form. Y equals slope times x. Slope is up 1 over 1, up 1 over 1. So that makes sense because the y is now the x and the x is now the y. So when you reverse it, the line of reflection is y equals x.
Always, no matter what.
In an inverse function, yes. Or an inverse relation, but that's how you would graph it. Okay, so if you use the graphing calculator, GeoGebra, or whatever, you're basically reversing the x and y. Now this is where it gets easy. So if I were to tell you, the only thing I have to do to tell you if I give you a function like y equals 2x plus 5, all you have to do is switch the x and y. So y equals 2x plus 5, the inverse would be x equals 5y, 2y plus 5. Did I say that right? So all I'm doing is putting the y in for the x and the x in for the y. And then I've got like x equals something, 2y plus 5. So then I have to solve for y. So get rid of the 5, divide by 2. And so the inverse function and the function need to be written with y by itself. But so that's where it gets easy. Now let's do this. We're not going to do that. Let's do example 2. So I'm going to find the equation for the inverse of y equals 2x plus 6. That's what we just talked about. So let's do that. So here's example 2. Y equals 2x plus 6. The only thing you have to do now is switch the x and y and then solve for y. So x equals 2y plus 6. Any questions with that so far? Okay, so now solve for y. How do you solve for y? How do you solve for y?
Get that on its own side.
Get the what?
Get the y on its own side.
Yeah, so we have to get this y by itself. So let's get rid of the 6. So now 2y equals x minus 6. Now what? Divide by 2. So then I'm going to get y equals 1/2 x minus 3. So there's the inverse function of y equals 2x plus 6. Now, just for the fun of it, let's graph this. Y equals 2x plus 6. Go up to 6 and go up 2 over 1. Looks like that, right? That's what y equals 2x plus 6 looks like. Let's graph y equals 1/2 x minus 3. Down 3. 1/2 x goes up 1 over 2. So it looks like that. Is that consistent with what we talked about? Remember, this is the line axis of symmetry. So that looks like a good reflection over that line, y equals x, that diagonal line, y equals x. Okay? All right. So the horizontal and vertical line test. So now you can do a horizontal line test to see if the inverse function is a function. Okay? So sometimes you will have a relation that's not a function, but when you invert it, it's now a function. So for example, this parabola, if I invert it, it looks like this. Right? I just reflected it over the x equals y equals x line. So if I would have started with this is not a function, or this is a function. No, this is not a function, but this is, because the vertical line test makes that not a function, but when you invert it, now it's a function. So I could do the horizontal line test. Well, this is a function because the vertical line test works. But the horizontal line test does not work because it's hitting both of those. It's hitting two at a time. So the inverse is not a function. Okay. All right. So let's complicate it just a little bit. It's not really too complicated. Remember, the process is switch out the x and y and then solve for y to find the inverse function. Okay, so let's do that on example 3. Here's example 3, y equals 1/4 x cubed minus 2. Okay, no problem. Let's reverse the x and y, right? X equals 1/4 y cubed minus 2. So let's get y by itself. What do you want to do first? Okay, so add 2, both sides. At this point, I'm going to switch sides. That makes me feel better. 1/4 y cubed equals x plus 2. Everyone okay with that so far? Now what? Divide by 1/4, which is the same thing as what? Multiplying by 4. So that whole thing by 4, remember, not just the 2 there. So then you get y cubed equals 4x plus 8. So far, so good. Now what? How do you get y by itself?
Decube it.
You cube root it. That's right. So we're going to cube root both sides, right? That's how you get rid of a 3 exponent. You apply a 3 root. Cube root. So then you're pretty much done. Cube root of 4x plus 8. That is your answer. Okay? So really, when it's more of a quadratic or a cubic equation, I mean, you're just going to have a radical in there somewhere. But that's okay, because you don't really have to do much else with it. I mean, you could try to graph it, but usually you could use a graphing calculator or a graphing website to do that. But all right, now there is. Let's do one more example, and then I'm going to show you. Sometimes there has to be restrictions to a domain, because you can't just put, especially when you find the inverse of a quadratic equation, you're going to have the square root of something, right? When you find the inverse of a quadratic equation, you're going to have like y equals a square root of something. What can't you take the square root of?
0.
You can take the square root of 0. Square root of 0 is 0.
A negative number?
A negative number. So you have to set restrictions, just like when you can't divide by 0. There's exclusions, right? Well, that's not, I mean, dividing by 0 is not even not any kind of imaginary number either. You just can't do it, okay? But if you want to keep yourself in the real world and not the imaginary world in Algebra 2, then you have to avoid dividing by or taking the square root of negative numbers, or any even root of negative numbers. So let me show you an example, and then we'll be done with that. So 2 steps: defining the inverse, reverse the x and y, and solve for y. That's it. Okay, so we are going, in example 4, we are going to restrict the domain of y equals x squared plus 2. We're going to restrict it so that the inverse is a function. So the inverse remains a function. Okay, this is a little different because this is what is the x squared plus 2 is basically this. Parabola up 2 places, right? That's y equals x squared. Do remember the mother function of parabola is y equals x squared, which is in the vertex, parabola at the origin. Plus 2, that's a vertical shift. All right, so the inverse would look like this. Right? Now, this is not a function because this, starting here is where you get 2 when you do a vertical line test. So we want to be able to get rid of this. So we want to restrict the domain so that it just is going that far. Okay, so let's figure that out. Now, you don't have to do this graphically. It's a lot easier to do this algebraically. So if I say that x is greater than or equal to 0 here, then it's only going to reflect, it's basically not going to do that. So if I say if x is greater than or equal to 0, graphically you can look at that and say, so none of these y values are going to reflect. So this is not going to come over here. So that's okay. But let's do it algebraically. So let's find the inverse. So the inverse looks like this. Inverse is x equals y squared plus 2. Let's get y by itself. Get rid of 2, get rid of 2. Y squared equals x minus 2. So y equals the square root of x minus 2. Okay? So now you just have to say what x is going to make that under part of the radical negative. Can you see it? Well, think of an x. Think of any number. Pick a number between negative infinity and infinity. Go.
Negative 72.
Negative 72 minus 2 is negative 74. Can you take the square root of negative 74? No. Let's get a little closer to here. What if x was 0? If x is 0, that would be negative 2. Square root of negative 2, still a negative. So 0 doesn't work. 1 doesn't work. But 2 would give you 0. Can you take the square root of 0? Okay, so do you see how any x under 2, you would end up with a negative number underneath the radical. So that will break the machine. So basically, we have to say that x has to be greater than or equal to 2 for this to work. Okay? Yep. So it's a lot, I think it's a lot, than trying to do this graphically, it's confusing. But if you just create the inverse function, so work out the inverse function, switch the x and y, solve for y, and then see what will break it. And we did this in Algebra 1 towards the end of the year, but basically you can't take the square root of a negative number. So what x will make that negative? Anything less than 2 will make that negative. So that's what we don't want. So we have to pick values that are greater than or equal to 2. Okay? So here's how I would write my solution. So if we remove domain, okay, so if I did this, then my range, so this is my domain. My domain has to be this domain, and you can just say colon. And then your range, what is your range going to be? Your range is always going to, it's just going to be positive numbers. So it's going to be greater than or equal to 0. So you don't have to graph it, because if you just plug in all the x's greater than or equal to 2, this will never go below 0. So the square root of a positive number when you're doing radical equations is just positive, even though there's technically two, but not when you're dealing with relations and functions. Okay, that's basically it. The application, distance, time, and gravity. You know, your distance equals rate times time. But when you're falling, the Sears Tower in Chicago is 1,451 feet tall. Anyone been to the Sears Tower? It's frightening. I was there when I was a kid. I was terrified. I went there when I was like 20 something. I was still terrified. So it's a long way up. 1,451 feet tall, the distance traveled by a free falling object. Have you guys heard that thing where if you drop a penny from the Sears Tower and it landed on somebody, it would kill somebody?
The Empire State Building.
Or the Empire State Building. But Sears Tower is technically higher than the Empire State Building, but yeah. So the distance, so a free falling object is given by d equals 16 times t squared. Okay, so where d is the distance in feet and t is the time in seconds. So how long would it take an object to reach the ground if dropped from the top of the Sears Tower? So basically you have to reverse. You have to solve for t instead. So t is actually the square root of d divided by 16. Okay. So then it ends up being 9.5 seconds to drop. Is that right? Only 9.5 seconds to drop a penny? Because it accelerates. You know what I mean? What's the maximum acceleration? Wasn't it like 9.8 meters per second? Seconds?
That's just
gravity.
the acceleration
That's just-
of gravity.
okay.
The penny is limited by air.
Yeah. Cool. All right. See, I did physics. I don't like math applied to my life.
Yeah.
So, all right. Good.
Black math. Give me some math and I'll give you some flack. Black math.